first problem, and I want to know what is the acceleration produced in this picture. So I have an object, let's just say it's a box sitting on the floor, and it has a mass of 30 kilograms. That's about 63 pounds. And I've got two forces that are acting on it. So let's say that there were two ropes on this box, and one person's pulling in one direction, one person's pulling in another. Or it could even be one person is trying to pull the box, and this is friction working against them. The practice problem that you have, that's actually the situation. Someone is pushing a box on the floor, and friction is working against them. Okay? So the very first thing we need to do is to figure out the net force. Because remember, our equation is that the net force equals mass times acceleration. Okay? So that's supposed to be F net. So the net force is the one force that replaces all of the other forces. Okay? And we have two forces, so we have to figure out what that net force is. Now remember that the net force is going to be equal to, that was a mistake. The net force is going to be equal to all of the applied forces. We'll call it FA. So all the forces that are trying to make it accelerate, make it go faster, minus all of the opposing forces, and those are all the forces that are trying to make it go slower or stop it. So in this problem, this right here, this is going to be the applied force. Okay, I'm pulling on the box, I'm pulling with 90 newtons. This is going to be the opposing force. Let's say that's friction, it's trying to slow me down. So this would be 90. This would be 30. And so the net force, the one force that replaces all of the other forces, that would be 60 newtons. And it's 60 newtons pointing to the right. So now I can plug it into this equation because I know the net force, it's 60 newtons. I know the mass, that's 30 kilograms. So all I'm left with is trying to find the acceleration. And then someone either shout out or write in the chat, how am I going to find A? How do I get A by itself?
Don't you divide by 30?
Yep, that's exactly right. So I'm going to divide both sides by 30. And I divide this side by 30. Those disappear. And then I'm left with the acceleration. Hopefully you guys don't need a calculator for that. 60 divided by 30 is 2. But if you don't feel comfortable writing down your answer out of your head, plug in the calculator and check. So the answer is 2 meters per second squared. Now, if you just used the force that you were pushing with, you would have got 3 meters per second squared. That's not what the acceleration was, because we had this other force that was trying to slow us down. Okay, so this is very, very, very similar to a problem that's, I want to say it's like number 7. I can't remember. I'm not looking at the sheet right now. Where you have a box and there's an applied force and there's friction. You have to find the one force that replaces both and then plug it into F equals ma. So a lot of these problems, you guys, they're going to be two-step problems. Okay. And that leads me to the next problem. So let's do one more. Maybe this was number 7. I can't remember. The ones near the end of your practice problem set, they were problems where you had to use your old acceleration equations along with our Newton's law equation. So let's figure out what this problem's telling us. So I'm teeing off, and I have a 46-gram golf ball. So the grams, 46 grams, what is that, you guys? That is the what of the golf ball?
mass?
It is. It is mass. Now, in chemistry, we use grams because we always work with like really small samples. In physics, we're going to use kilograms. So we have to divide this by 1,000. Or I think, you guys learned last year in chemistry, I don't know if you remember it, that you move the decimal to the left 3 places. I can review that with any of you that want that, but I'm going to write down the mass is 0.046 kilograms. All right, so I have this golf ball. It's in contact with the club for 1/10 of a second. So when I'm swinging my club and I hit that ball on the tee, it stays on my club for 1/10 of a second. So that'll be my time. Now, if you know about golf, how fast is that ball going before I hit it when it's on the tee? What's the starting speed? Nobody?
0.
It's 0. That's right. Golf would be a lot harder if the ball was moving it and I had to try to hit it. So the starting speed is 0, and then the ball leaves the club with the velocity of 24. So that is going to be its final velocity. And what the question is asking is it's asking what is the force that was applied to the ball. So, this is something that we're going to be talking about again, you guys, but just be aware that the only time that an object is accelerating or the only time that an object is changing its velocity is when you are applying a force to it, right? That's what Newton's first law says. So Newton's first law says if there's no net force, then an object maintains its state of motion. It maintains its velocity, keeps moving at the same speed in a straight line, or it remains stopped if it was stopped. So the only time that this ball is going to be accelerating from you hitting it is when the club is actually physically touching the ball. All right. The fastest that golf ball will be going for its entire flight is actually when it leaves the club head, like at that moment in time. After that, it'll end up at almost the same speed, but because of air resistance, it'll actually be going slower when it hits the ground. Okay. So if I want to find the force, we're going to assume that there's only one force acting on that. That's the force of the club. And we know that net force is mass times acceleration. Okay. Well, we know the mass. But what we don't know is this acceleration. But we have, I think, all the information we need to find it. So if we take these 3 variables and we use them to find A, once we find the acceleration, then we can plug it back into this equation. So these problems, they're 2-step problems. Okay, we're really going to have to use our brains to figure these out. And once again, I told you that if you're lost in that first unit, if you need help with the acceleration stuff, you need to ask, because it's going to keep coming up all the way till the last day of physics at the end of the year. So I look at my equation sheet, I look over my list, and I see, okay, I have A, VF, VO, and T. And if you look at your sheet, there's an equation that says acceleration equals final velocity minus original velocity divided by the time. And so we're going to say it's 24 minus 0. Excuse me for not putting the units in, you guys. It's too much, it's too little. And that's divided by 0.1. So 24 divided by 0.1, if you punch that in your calculator, it'll end up being 240 meters per second, or meters per second squared. So now I have acceleration and I have mass, so now I can figure out net force. So my net force is going to be 0.046 Once again, I did not give myself enough room to even write the units, so I'm sorry. But 0.046 kilograms times 240 meters per second squared. And you know what? I'm going to need to punch that in my calculator, or someone could do it for me, because that's math that I'm too tired to do in my head this morning. So 240 times 0.046. So I get a force of 11.04 newtons. So once again, two-step problem. If you look at those practice problems that I assigned you on Wednesday or Thursday, I can't remember which day. At the end, they're all basically two-step problems. So you're going to have to use your acceleration equations and your net force equations. So does anybody have any questions at this point about those problems? You want me to do another one? Do you feel good? Can I get some thumbs up or?
Another one.
Sure, we can do another one. You want to do one right from your sheet?
No, you could just pick one.
Okay. Well, you know what? I'm gonna pick one from your sheet. Actually, I'll just one. Oops, that is the wrong thing. That's not what I meant to grab. So let's pick. We'll go one near the end. All right. This looks like a good one. So we'll do number 11. We'll pop this in here. So this is right off your homework, you guys. I have an airplane, and it's getting ready for takeoff. Starts from rest, and it reaches 55 meters per second in 3.5 seconds. What force do I need to accelerate it? So let's write down everything we know. We have 8,000 kilograms for the airplane. We know that's the mass. You guys told me that last time. Okay. We know that the airplane, when it's taking off, it starts from rest. So we know its starting speed. It's going to be 0. So this problem is actually a lot like the last problem. Seeing a pattern here. It needs to reach 55 meters per second to take off. So its final speed is going to be 55 meters per second. And it has to do that in 3.5 seconds. Now the reason it has to do it in 3.5 seconds is because the runway is not an unlimited amount of space. So this must be tied to the distance, the length of the runway. Instead of asking you instead of giving you the time, I could have given you the distance that it has to go. But we would have gotten the same answer. And then it asked me, what is the force? So the force is the question mark. All right. Now, if you write that stuff down on your test, that's 4 out of 10 points. Okay, so you almost got half credit. And we know we want to find force, and we have one equation right now for force, and that is that the net force is equal to the mass times the acceleration. Okay, I have the mass, but I don't have the acceleration. But I'm going to use this information right here to find my acceleration. So this is another two-step problem. And I look at my equation sheet and I say, okay, well, which equation should I use if I have acceleration, original speed, final speed, and time? And the easiest one, the one that I don't have to do any algebra for, is that the acceleration is the final velocity minus the original velocity divided by the time. So So I'll plug that in. Oop. Oh, I don't know why I keep doing that. Okay, so the acceleration equals 55 minus 0. Excuse me again for not writing the units down. And then the time is 3.5 seconds. So I punch that in my calculator. I get 55 divided by 3. That will be 18.3 meters per second, or meters per second squared. So that's my acceleration. That acceleration is going to get put right here. So that's going to go over here. And then I have the mass of 8,000. So my net force is going to equal the mass of 8,000 kilograms. I left myself enough space to write it. Times the acceleration, which is 18.3 meters per second squared.
I have a question.
Yep.
Wouldn't it be 15.7?
Oh, did I punch it in wrong?
I think you just put in 15 divided by 3.
Yeah, because I got the same thing.
Wait, what? Oh, I'm sorry. You're right. I did just put 3. Oh, thanks, you guys. That makes me feel so much better, because I know that you're following along. All right. So wait, I'm sorry. What was it? 15 point what?
15.7.
15.7. Thank you so much. That is exactly what I did. All right, so that'll be 15.7, and now I would just plug that in my calculator. And you guys are going to have to check me. I got 125,600 newtons. Did everybody get the same thing?
I got that.
Okay, awesome. So 125,600 newtons. And actually, so you saw, anybody can make a calculator mistake, or anybody could, do something silly. On your test, you guys, if you did what I just did, the lowest grade you would get is a 9 out of 10. Remember I told you this answer, the numerical part of this answer is kind of the least important thing to me. The most important thing is all this thinking. So if you made that mistake, just between you and me, I probably would just give you 10 out of 10. Because that is just a silly punching it in the calculator wrong. Everything else here was right, so I would just give you full credit. Does that make sense to everybody? Because it's the process that's the most important to me, not the quote unquote, right answer.
I have a question.
Yeah.
Could you go back to the other equation? I just want to see something.
This one?
Yeah, the one we did before it.
Okay.
Okay, thank you.
Oh, you're welcome. Yeah, so those two problems, you guys, they were very similar to each other. If you see that we ended up using the same equations. But it won't always be this acceleration equation. Remember, we have 4 of them. So it could be this one. It could be VF squared equals VO squared plus 2AD if there's no time. It could be that the distance equals VOT plus 1/2 AT squared if I'm not given the final velocity, but I'm given time and distance. I might ask you to solve for a final velocity. So I might give you the force and the mass, make you solve for acceleration, and then you could use VF equals VO plus AT. So it just kind of depends on the situation. And the way you get better at this stuff is just by doing more practice. And don't forget, all of the answers They're in Schoology, so you can check your answers. And then Mr. Hammond has made videos, practice videos, where he goes through a lot of these problems. And you can always look back at this. And I have office hours, like, I'm here for you. So can we, do you want to go over our new topic for today? This won't take too long. I don't think it'll blow out your brains too much. So let's do one new thing today. And that's basically talking about Newton's third law. Okay, so this is what Newton's third law says. It says that for every action force, there is an equal and opposite reaction force. I'm pretty sure that the vast majority of you have heard this in physical science or middle school science, or, you know, I don't know, watching Little Einsteins or something. So once again, for every action force, there's an equal and opposite reaction force. That's all it says. Now, another way of thinking about this, you guys, is that you can't ever hit an object harder than it hits you back. So let's say that I'm a soccer player and I'm heading a ball. As hard as I hit that ball, the ball is going to hit my head. So the action force here would be my head hitting the ball. The reaction force is the ball hitting my head. If I hit the ball with 200 newtons of force, the ball is going to push on my head with 200 newtons of force. Now it's the same for this football player here. So we have this defensive player, looks like an Alabama player to me, and he's putting a hit on a Clemson player. Now, if you look, they're hitting heads. So this player, the action force would be the force of his helmet on the Clemson player's helmet. The reaction force would be the Clemson player's helmet on his helmet. This player can't hit this player any harder than he gets hit back. Now, you know, I don't know if all of you have been following this, but especially with sports like football, there's been a lot of concern about concussions, and this is the reason. Anytime two players hit, you know, the one player is getting just as much force as the other player. If they hit head to head, both of these players can get a concussion because they're both taking a force to the head. And in a lot of, when I was a kid and we played football, like, everyone wore knee pads. So you would have a knee pad down here, it would be covering your knee, be a little cushion. And when someone hit their head on your knee, there was less force on your knee and less force on their head because of that pad. But right now, and we'll explain that has to do with momentum and impulse later. But right now, because nobody wears these knee pads anymore, they slow you down, they don't make you as fast. If you hit your head on someone's knee, you can sustain a concussion because, once again, I can't hit any object harder than it hits me back. So if I hit his knee really hard, with a few hundred newtons of force, my head is going to sustain a few hundred newtons of force. So in sports like soccer, where you're heading balls, in sports like football, where you're hitting heads, you know, it's a real concern. If you don't head the ball properly, or if you don't tackle properly, that you can get concussions. And these forces build up over time. Now, you guys might know that, you know, this is never a good situation. All right, hopefully this isn't you. But there are people that when they lose their temper, they can't control themselves. So one of the things that people can do, I've seen it happen, is that they get really mad and they punch a wall. All right. Now there's two outcomes when that happens. The luckiest outcome is you punch the wall and you put a hole in the drywall. Okay. Um, the unluckiest outcome is that behind where you punch, there's a wooden stud that's helping to hold up the wall, and you punch that wooden stud and you break your hand. There's no hole, right? Now, why does that happen? Why does one part of the wall break and the other part of the wall not when I was trying, like my arm was pushing with the same force? Anybody have any ideas? Nobody wants to put themselves out there? Well, I'll let you know. Drywall, it can't sustain as much force, right? So I can't actually apply as much force to it. So even though my muscles are trying to push hard, when I hit the drywall, I can only apply whatever force to it before it breaks. So maybe let's say that's 50 pounds. Now, probably won't feel good. Maybe I have bloody knuckles, right? But because the drywall can only sustain 50 pounds of force, my action force would be 50 pounds of force hitting the drywall. The reaction force is 50 pounds pushing back on my fist. If I hit where the stud is, that can sustain way more force than I can deliver. So even if I put all of my body weight into it and I punch it with 200 pounds, the action force would actually be all 200 pounds hitting the wall. The reaction force, 200 pounds hitting my fist. And so this is why in real life, usually when there's a fight, a physical fight, which is always upsetting to me and I don't like to see that, they usually last a very, very short time. Because the bones in your hand, they can't sustain a lot of force. And if you hit someone really, really hard, especially in the head, you don't hit them in the nose, you hit them like on the top of the head or the forehead or something, their skull can sustain more force. So the most likely outcome is that you break your hand. Yeah. But hopefully you guys have never experienced that, but that's all a direct result from Newton's third law. Now let's look at some other less violent examples, all right? So we just said that for every action force, there's this equal and opposite reaction force, right? If we go back here, I have the action force. The action force is my head on the ball. The reaction force is the ball pushing on my head. Those forces are equal and opposite. So if I pushed on the ball with 100 newtons, that means that the ball is pushing on my head with 100 newtons. So they're exactly the same forces in the opposite directions. So now, if I look at these examples, let's first look at a bat hitting a ball. So I have a bat. It's going to hit a baseball. The action force is the bat hitting the ball. Can someone tell me what the reaction force will be?
The ball bouncing off the bat.
Right. The reaction force is going to be the ball actually hitting the bat, right? So the bat's going to hit the ball, force is going to go on the baseball. The reaction force is the ball hitting the bat, and that force is going to push backwards. Okay? Now, if these forces are exactly the same size, then why doesn't the net force equal 0? Because if the net force was 0, the baseball wouldn't go anywhere, right? It would have 0 acceleration. But when you hit a baseball, it actually does change its velocity. It starts moving in the opposite direction from where it was heading before. Does anybody have an idea? And don't feel silly telling me.
They cancel each other out.
Well, yeah, you would think they would cancel each other out, right? But if they did cancel each other out, then that ball wouldn't move, right? There wouldn't be any force acting on it. So they don't actually cancel.
Is it because they have different masses?
That's a really good thought. It is a good thought, but it's not quite right, because even if the net force was zero, then like literally nothing would move no matter what the mass was. But I love your thinking, you two. I'm just gonna let the cat out of the bag right now. So if we look at this force was the bat hitting the ball, right? So this force is acting on the ball. So this force right here is acting on this ball right there. Now this is the ball hitting the bat. So this force is acting on the bat. So those two forces, they're not acting on the same object, right? One force is going to the ball, the other force is going to the bat. Because they're not acting on the same object, you guys, they don't cancel each other out. In order to cancel out, they have to be acting on the same thing. Like if I have a box and I have two ropes tied to it, and or a rope, and I'm doing a tug of war, well, now the forces are acting on the same object. They're acting on the same rope. They're acting on the same box. But these forces are not acting on the same object. One force is on the bat, the other force is on the ball. And if you've ever swung a bat really hard at a hard ball, which I think most of you probably had at some point in your life, or you have, if you don't hit that ball just right on what's called the sweet spot of the bat, what happens is this reaction force on the bat can actually make the bat vibrate, and it does not feel good. Right? It like makes your hands feel bad and your arms. So that's the reason. That's the reason they don't cancel each other out. They're actually not acting on the same object. One's on object A, one's on object B. So I don't know if you've ever had anybody tell you before, when they were trying to teach you something, like, this isn't rocket science. Well, Newton's third law, this is rocket science. Okay, this is how rockets work. So in this case, the action force, if I have the space shuttle, the action force is the rocket pushing on the exhaust gases. So when the shuttle launches, it pushes the gases down. The gases are going to do what to the space shuttle? So if the action force is the rocket pushing the exhaust gases down, the reaction force would be
To go up?
right. The reaction force would be the exhaust gases pushing on the rocket up. So once again, these two forces, they're equal and opposite, but one force is acting on the rocket, the other force is acting on the exhaust gases. So the exhaust gases get pushed down, and in turn, the space shuttle gets pushed up. So this is how we launch rockets. This is how every rocket works. It's how jet engines work on airplanes. So the jet engine on the airplane, it pushes the air backwards, and the air pushes on the jet engine forwards. If you have a propeller, it does the exact same thing. The propeller pushes the air backwards, the air pushes on the propeller forwards. So this is all because of Newton's third law. For every action force, equal and opposite reaction force, and the forces are acting on the two different objects. So this would be a good test question. I'll give you this question. I'm driving down the road at 50 miles an hour, right? It's it's night. I'm out in the middle of the cornfields, right? Maybe I'm going to Illinois State or Champaign or uh, one of those places in central Illinois. Lots of bugs. So I'm driving down the road. I squish a bug on my windshield. Which feels the bigger force? The bug getting squished or my windshield? So everyone just keep that in your head for 1 second. And then I want you to write it in the chat box. So write in the chat box, which feels the bigger force? The bug getting squished or my windshield? So I have one answer, two. Getting a lot of answers. I feel like you guys are feeding off each other. So let me ask you this question. Which feels the bigger force here? The baseball or the bat? Aren't those forces equal and opposite? So wouldn't they be the same? And then right here too, which would feel the bigger force, the exhaust gases or the rocket? They would be the same. So if I squish a bug with my windshield, the action force would be my windshield hitting the bug. The reaction force would be the bug hitting the windshield. Those forces, you guys, have to be equal and opposite. So they would both have the same force. The reason the bug squishes and the windshield's intact is just because the bug can withstand less force than the windshield. But if you've ever been on a motorcycle without a windshield, or like a dirt bike or something, and hit a bug hard, or even if you've ever stuck your arm out the window and had a bug hit you when you're going down the highway, it hurts. Right? So but the force is equal and opposite. As hard as that bug hits your arm, you hit the bug back. Equal and opposite. All right, one more thing, and then I'm going to cut you guys loose. So I want to know why this situation here won't work using Newton's third law. So just so you guys know, usually how we introduce this topic, if we were at Leiden, and I know you're probably sick of hearing this, is I would give you a bunch of materials, and I string a line from the back of the physics room to the front, and we have a contest to see who could build a like a balloon car that goes from the back to the front. Whoever hits the front of the room first gets a prize. It's usually extra credit on your test, but so basically, lots of people try to make their balloon cars like this, where they fill up a balloon and then they put a piece of paper in front of the exhaust as a sail, and they're thinking that this is a big fan, by the way, and they're thinking that the air leaving this fan, right, the air that's pushing out of that fan is going to push on this sail, and it's going to make the boat go forward. The problem here, you guys, is that if you try to do this, it won't work. It won't go anywhere. All right? And this is why. There's a whole bunch of, there's actually two different sets of action-reaction forces here. So the first set of action-reaction forces is I have the fan pushing the air. And then the air is going to push on the fan. Then I have the air pushing on the sail over here, and the sail push on the air back. The problem is that all of these forces, they're all acting on an object that's the same object. So in this situation, remember when I said before, um, why wouldn't the net force be zero? And I said, well, that's because these action and reaction forces, they're acting on different objects. In this situation, the action and reaction forces are acting on the same object. They're acting on the boat. So this boat ends up going nowhere. How would I change this? Yeah, and I'm glad that someone actually wrote that down. So how could I change this so that it actually worked? So you could break the boat in half, and the way I would break it in half, I wouldn't actually break it in half. I would remove the sail. If you get rid of the sail, then you get what we call a fan boat. You may have seen these in movies. All right. Um, this fan, what it does, right? The fan is pushing the air in one direction. The fan is pushing the air backwards, and the air is pushing the boat forwards. So if I turn this fan around and remove the sail, now all of a sudden it works. And they use these boats, you guys, just so you know, they use them in places that are really swampy because those swamps aren't very deep. And you can see this thing is called the John boat. It doesn't go very deep in the water. And if I have the fan, I don't have to have a motor that's going to get stuck on rocks or the bottom or seaweed. And it just pushes the boat around forward. So these fan boats, we use them in the American Southeast. Florida, Louisiana, Georgia, places like that, where it's swampy and not too deep. And this works because of Newton's third law. This doesn't work for the same reason.